Okay, so it's 3 p.m. and since no one else is here, so I'll wait for a few minutes and probably then get started. Okay, I'll wait for a couple of minutes and I'll just uh, solve some problems in this session since no one is here. All right, so I'll get started anyway since no one is here. So, if you are seeing this video later on YouTube, so welcome to this fourth week of TS session. This is on multivariable optimization. I'm Rita Branath from ISC Bangalore. So, I'll be discussing some of the topics that's already been covered in this week's content. So, like Newton's method, Stefan's descent method, univariate method, convexity, and I'll take some example problems and try to solve it in the class. So the goal of this session was to have this solved with you only, like I'll be giving some problems to you and you'll be solving with me. But it's really disappointing that no one joined. So I don't know. So I hope you are solving your assignments on time and you're finding it easy to solve this probably, but bear in mind that I might discuss something or might skip something if you don't attend these sessions from next time onwards, and that might be a problem for you later on. So if you're watching this video later, so keep this on mind. Anyway, so I'll get started with the class. So the first topic that I wanted to cover is Newton's method for multivariable function. And problem, this method was not covered in the lectures that was posted because I think sir covered only Newton's method for single variable functions. But I think you'll find some problems related to multivariable functions as well, and you have to solve those using Newton's method. So I'll be discussing this at first. So let's get started. So what do we do in Newton's method for a single variable function? So I'll write it down. So there, the update rule is x t plus 1 equals xt. Then you have minus of f prime fxt divided by f double prime of xt. So you need the first and second derivative to calculate that. But right now what we don't have a single xt that you need to keep in mind. So what we have is a vector here. So that's why I've written it in bold. And similar to the f prime xt term, I have the gradient here. And similar to the second derivative of the single variable function, I have the Hessian matrix here and I have to take the inverse of it. So that's why I have written the expression like this, and then I have a minus sign before it, and you can also have some step size to have this. So this equation, you can derive it similarly like Sir derived in the class. There, the condition was to, for single variable function, the condition was to have f prime xt that vanishes at that point. Here, you will have the condition as for optimality delta of fxt equals to 0. So by similar argument, you can prove this. I'm not going into the proof of this. The goal of it is to just solve some problems. So let's get into the problem setup. So this is the optimization problem that I have. I have to minimize a function of two variables, x1 and x2, and I have to solve it using Newton's method. Now you can see that this is a multivariable problem, and I have given my initial point as minus 3 comma 1. So how can we solve it? So as I have already mentioned, you have this equation xt plus 1 equals xt minus h inverse of xt delta fxt. So as you can notice, for t equals to 0, your x0 is given. You need to find out x1. And for that, you need to calculate both your Hessian and your gradient. So let's do that. So your fx function is given as x1 square minus 4x1 x2 plus 9x2 square. And you have to find the gradient of this function. So let's try and find out that. So this is nothing but 2x1, and the second term will be, okay, so yeah, finally we have someone who joined the meeting. So probably I'll just go through whatever I've discussed till now. So I'll be taking some example problems and solve it in the class. So the assignment problem probably have some problems related to multivariable functions, and using Newton's method, you have to solve it. And for a single variable function, you have this kind of a formula. But for a multivariable function, I think Sir did not teach this in the class. So what you have, similar to the update rule for a single variable function, instead of the first derivative of the function, you have a gradient here, a gradient of fxt, and instead of the second derivative of the function, you have the inverse of the Hessian matrix. So just keep this in mind, and I think you'll be able to solve this problem that I'll be discussing now. So my problem is minimize fx equals to x1 square minus 4x1 x2 plus 9x2 square. And I have to solve it using Newton's method, and this is a multivariable problem. And my initial guess x naught is given as minus 3 comma 1. So first I have written this formula for a multivariable function update using Newton's method. And as you can notice is that I have to find out my gradient and Hessian matrix. So that's exactly what I'm doing right now. So this is your function. My gradient will be 2x1 minus 4x2. And the second term will be minus of 4x2. Sorry, that will be minus of 4x1 because you are taking the derivative with respect to x2 plus 18x2. So I hope I have written this correctly. So this is your gradient, and then you have to find out your Hessian matrix, and your Hessian matrix will be nothing but the first term will be 2, this term will be minus 4, then this term will be minus 4, and this term will be 18. So the next step is to find out the inverse of the Hessian matrix. That you can find out using a simple rule, which is you can write it as H inverse of H equals to identity. And what you can do, you can assume four terms of H inverse as A, B, C, and D. And your H is nothing but 2 minus 4. This will be minus 4, and this is 18. And this will be equals to 1, 0, 0, 1. So if you evaluate this, you will probably get 2a minus 4b. This will be your first term. Your second term will be uh, minus 4a plus 18b. This term will be 2c minus 4d. This term will be minus 4c plus 18d. And this will be equals to 1, 0, 0, 1. Now you just have to solve this equations and you will get your answer. So what you have is that 4a equals to 18b. So your a is 9b by 2, and you have 2a minus 4b equals to 1. So you can put the value of 2a as 9b minus 4b equals to 1. So your b is nothing but 1/5, and your a will be 9 by 2 times 1/5. So this is 9 by 10. So let's solve for C and D. So what you'll get is 2C equals to 4D or C equals to 2D. And your minus 4C plus 18D equals to 1. So if you put C equals to 2D here, you'll get 10D equals to 1 and D equals to 1 by 10. And similarly, your C will be 1 by 5. So let's write your Hessian matrix now. So your H inverse is nothing but your A was 9 by 10, your B was 1/5, this was, what was this? 1/5, C is 1/5, and your D is 1/10. So you have got your H inverse, and now you have to just plug in this minus 3 and 1 and, as the point. So you'll get H inverse of X naught. So let's write it down. So H inverse of X naught will be this only because you don't have any terms related to X1 and X2. And this gradient, if you plug in the value of minus 3 and 1, you will probably get 2 times of minus 3 minus 4 times of 1, and the second term will be minus of 4 times of x1, which is minus 3 plus 18 times 1. So this will be minus 6 minus 4 minus 10, and this is minus 12 plus 18, so that will be 6. So let's plug all these values in this equation and try to find x1. So what will be your x1? So your x1 is x naught minus h inverse of x naught times delta of f x naught. So your x naught was minus 3 and 1. Then I have to put this h inverse term here. And finally, I have to put the gradient value here. So the gradient value is minus 10, 6. So let's multiply the terms and try to find out the answer. So this is minus 3, this is 1. And the next term will be, this is 9 by 10 times minus 10. So that's minus 9. And then I have 1/5 times 6. So this will be 6 by 5. And then I have the second term, which is 1/5 times of minus 10. So this is minus 2. And then I have 1/10 times of this term. So this will be 3 by 5. So let me just check if my Hessian matrix is correct or not. So this is 2 minus 4. And then I have minus 4 plus 18. So let's multiply it with this if I get back the same thing. So this is 18 by 10. So that's 9 by 5 minus 5, 4 by 5. So that's fine. Then it was 9 by, so next is, yeah, minus 4 by 5. So that's correct. Then it's minus 36 by 10 plus 36 by 10. That's correct. Then it's 1/5. So this is 2/5 minus 2/5. That's correct. And then it was minus 4/5 plus 9/5. Okay. So your second update will be something like this. So this is minus 3, 1. And this term will be nothing but if you take 5 out of it. So this will be minus 39 by 5 if I have not done it wrongly. So that's fine, I guess. And this will be minus 7 by 5. So ultimately, what you are left with will be something like minus 3 plus of 39 by 5. So that's 39 by 5. So that's 24 by 5. And the second term will be 1 plus 7 by 5. So that's 12 by 5. So this will be your second update. And this 24 by 5 and 12 by 5, if you plug it in this equation, you'll probably get objective function value. Let me check how much you will get. So this will be, the second term is 12 by 5. So yeah, 4, 24 by 5 and 12 by 5. So you'll probably get an objective function of 28.8 or something. But again, this is not an optimal because you can check by putting this x1 value in the gradient, this gradient. If it doesn't vanish, then you have not reached your optimal. So this 2x1 minus 4x2, this will probably be 0. Then your minus 4x1 plus 18x2. So let us try to calculate that. So that part won't be 0. So your second term here is not 0. So it will in fact be something like 24. So you have not reached optimality yet and you have to go for more iterations. So I'm not going into more iterations because The goal really is to solve these problems by yourself. I'll just then guide you. So you go with the similar approach with the second iteration, and after that, you have to just check the gradient value. If it vanishes, then you have reached an optimal point, and this Hessian matrix, I think, will become positive semi-definite. So you can say that it's a minima point. So I'll not complete the whole problem. I have just shown you iteration one. So the rest part lies with you. I think you'll get some similar problem in the material as well, in the assignment problem. Okay, so let's now go into the discussion of steepest descent method. So the steepest descent method for multivariable function, the update rule is using this. Xt plus 1 equals to xt plus alpha dt, and dt is just the negative of the gradient direction. So with that, let's solve another problem. So I've given you this problem: minimize this function fxy x square plus 4y square, and solve this problem using the steepest descent method with an initial guess of x naught equals 2, 1. So let's try to solve this problem. So what you have, you need is this formula. Okay, so a few more people are joining in now. Okay, yeah, so your xt plus 1 is xt plus alpha dt, and your dt is nothing but negative of the gradient direction. So, okay, just a minute. Yeah, so what you can do, uh, you have this function and you can write the expression for, let me see how much space I have. Okay, I have a lot of space. So here this xt is nothing but a function of x and y here, and you have to plug those values in. So this gradient expression is 2x, and this one will be 8y. Okay, so what you can do now, you have your initial guess, which is 2 and 1, and you can plug those values in. So this is 2, this is 1, so this is nothing but 4 and 8. And now you can use the update rule. So your x1 is x naught plus alpha d naught. So your x naught is 2, 1. Then you have your alpha, and your d is minus of this gradient. So what you have, it's 2 minus 4 alpha and 1 minus 8 alpha. So what you have to do is now you have to plug this in the objective function, and you will get a function in terms of one variable only, and you can minimize that function. And that way you can obtain the optima. So let's do that. So what you will get is your 2 minus 4 alpha square. So suppose I write it as z plus 4 times of 1 minus 8 alpha whole square. So what you are left with is 4 minus 16 alpha plus 16 alpha square plus 4. Then you have minus 16 alpha times 4. So this is 64 alpha. And then you have 64 alpha squared times 4. So this is this. And you will have expression in terms of alphas. And it will be like this. So now what you have to do, this function is purely in terms of alpha, and you can minimize this function. So let's try to do that. Uh, okay, so I'll write it in the next page. So your g of alpha is nothing but 272 alpha square minus 80 alpha plus 8. Your g prime alpha is 270 times 2, so I think that's 544 alpha minus 80. And you have to set this to 0. So ultimately what you will be getting is 80 by 544. So this is 0.147. So if you plug this alpha values here and you will get your first update of x1. So this x1, now it's 2 minus 4 of alpha and then 1 minus 8 of alpha. So your first update values will be 2 minus 4 of alpha, that's 1.412, and the second term will be minus of 0.176. Yeah. So next, what you can do, again, you can plug these values in the gradient expression and you can see that those doesn't vanish. So you have to go for another iteration using the steepest descent method where your D2 will be again uh, calculated using the updated value of this gradient, which you can calculate, plug in, and then you can get it easily. So it's not like that you can get your solution in one step or something. You probably have to go for some more iterations to get the solution, and you can probably guess that in this case, your solution value will be at 0, 0 because this is an unconstrained optimization problem. And since these are sum up to square terms, then it will be in 0, 0. And if my initial guess is somewhere like 2 off or something, probably I'll have to do more iterations to get the solution. Yeah, so that's the idea behind the steepest descent method. And again, I have just shown you one iteration of it. You can have then multiple iterations to solve it. So I'm not will be solving this problem fully because I'll leave it to you so that you can solve it and get the answer and probably will get something like this in the assignment problem as well. So complete the rest of the part. So next I have, suppose the same problem using univariate method. So what I have is this function x squared plus 4y squared. So I have x squared plus 4y squared. This is my fxy. And I have my initial guess x naught as 2, 1. So in univariate method, we go for similar update. Yeah, so in this method, we'll go for similar update, but the gradient is a bit different here. Sorry, the direction is different. So first, we'll be optimizing along the x direction. So my dt at first will be 1, 0. And let's see how we can do this. So my x naught is given. So what I can do, I can have x1 equals x naught plus alpha times 1, 0. Your x naught is 2, 1. So this is nothing but 2 plus alpha, and this will be 1. So now what you can do, you can uh, plug this value back into the function. You will get plus 4y squared. So now if you minimize this function g alpha, probably you can guess that it's the summation of two terms. And if the first term, this term is constant, so if this goes to 0, you kind of minimize this function. So you can put alpha equals to minus 2. And if you put that, your x1, your update will be 0, 1. Similarly, you can get to the second point, x2. So for that, what you can do, can again use the same trick, but here you will optimize along the y direction. So your x1 here is, it has now become 0, 1. And your alpha is again 0, 1. So this term will be 0 and 1 plus alpha. So again, you plug this to the equation, the objective function, and you will get h of alpha equals 0 square plus 4 times 1 plus alpha square. Again, you have to minimize this, and you can put alpha equals to minus 1 to minimize this, and ultimately what you will get, your x2 is 0, 0. And if you calculate the gradient of this function, so this function is grad of fxy is nothing but 2x and 8y. So if you put 0 and 0 to this equation, so the gradient will vanish, and you can see that you can have reached an optima. And again, if you evaluate your Hessian matrix, you will get a positive semi-definite matrix, and you can say that you have reached a minimum point. So that's how we can solve this problem. So I've discussed using three methods. So complete those two by Newton's method and the steepest descent method. And the answer probably for all of this will be 0, 0. I have not shown you the entire steps to solve those two problems, which I have discussed earlier. Okay, so any questions related to what I have discussed right now? I know everyone joined a bit late, but yeah, please don't be late from next time because it gets difficult if you don't understand and join in between, so that will be a problem. So any questions related to anything like assignment, problem, or anything that I have discussed? Otherwise, I'll go on with discussing next few problems, see how much I can cover. Okay, seems like no questions till now, so that's okay. Okay, so I'll move forward to this problem. So next, okay, so some issue here. Okay, so I'll be discussing convexity. So I think in the second lecture of this week, Sir discusses about convex functions, and you probably maybe ask some questions that whether a function is convex or not. You have to check those. So let's see if we can solve this problem. So the function that we have given is fxy, which is a multivariable function again, x to the power 6 and y to the power 6. So we have to tell whether it's convex or not. And let's see how we can do that. Probably you can guess, since again you can write it in terms of a squared term. So this kind of takes a global minima value of 0, and anything like if you put some other values to x and y, it will always be positive. So since it's kind of you have a one global minima, you can guess that it's a convex function, and everything kind of lies above it if you join it by a straight line or lies below it. Okay, so let's do this mathematically. So let's try to solve this. So in order to check convexity, Sir discussed about Hessian matrix to be positive semi-definite. So we'll be using something like that only. So for that, we have to get to the Hessian matrix first. So let's evaluate that. So the gradient of this function is 6 x to the power 5 y to the power 6, and the second term will be 6 x to the power 6 y to the power 5. And your Hessian matrix H, that will be you differentiate with respect to x. So this will be 30 x to the power 4 y to the power 6. Next is with respect to y. So this will be 36 x to the power 5 y to the power 5. We'll get a similar term here. And then what you are left with is another term, which is 30 x to the power 6 y to the power 4. Now, what you can do, there are many ways of checking the positive semi-definiteness. You can take one vector, say A, then you can have A transpose H A. So if it is greater than equals to 0, you can say for certain that you have a positive semi-definite matrix. But as you can notice, the Hessian expression is a bit complicated here. So what we have to use is the signs of the eigenvalues, and to check the positive definiteness of this matrix. So we have one property that if all the eigenvalues of a matrix is non-negative, then that matrix is positive semi-definite. So we'll use that property, and we have another property that is your product of the eigenvalues of a matrix is equals to the determinant of the matrix. So we have to, if you just get the determinant of this matrix and then relate it to the eigenvalue, so that will be helpful in this situation. So let's do that. So let's find the determinant of this matrix H. So what you have is 30 square x to the power 4, y to the power 6, then you have another term x to the power 6, and this will be y to the power 4 minus 36 square x to the power 10 y to the power 10. So this will be 30 square x to the power 10 y to the power 10 minus 36 square x to the power 10 y to the power 10. So this will be 30 square minus 36 square x to the power 10 y to the power 10. And whatever you're left with in this portion is the negative term that you can notice. So probably what I have earlier thought about it being a convex function, it might not turn out to be that. So let's see. This determinant value, if you notice, it will end up being negative because anyway these terms cannot be negative because these are again a squared term of x to the power 5 y to the power 5. So this will be less than 0 for all x's and y's, less than equals to 0, I should write. So now what we have, if we have a situation like this, then you can say that if it's less than 0, then one of the eigenvalues has to be negative. Otherwise, the product won't be negative. So in that case, your matrix won't be a positive definite matrix. And on the other hand, if it's equals to 0, then you cannot say for certain if your x and y values are taking value 0. And then you cannot say for certain whether it's a negative definite matrix or a positive definite matrix. So in this situation, I think you'll have something similar to this. So you cannot say for certain whether this function is convex or not using this method as well. But I'll also like have some small doubt that this x cube and y cube. So only when this x and y is 0, so that will be a minima point. But then it's not for certain that you can say that whether this function is convex or not using this method, because as we have noticed, this determinant is indeed can turn out to be negative for some values of x and y. So, but probably I can like ask you, suppose I had given you a different kind of function. Suppose this is x square and y square. So in that situation, you can tell for certain because your this terms will be, this is 2xy square, and this second term will be 2y x square, and then it will be 2y square, and this will be probably 4xy, this is 4xy, and this will be 2x square, something like this. Again, in this situation as well, you might cannot say this for certain, but yeah, I think the best way of approaching this problem in those situations can be take some A equals A1, A2 transpose, and try to multiply this with H and then A. And again, I think you will reach some conclusion that with A1 and A2 value, again, you cannot say for certain this matrix turns out to be positive definite. So hopefully the function that will be given in your assignment will be more clear that you can say for certain whether a function is convex or concave. So pay attention to that, and you can use this techniques to solve this. So this problem, Newton-Raphson's method example problem, I'll come back to it if I have time because we have already seen this in the previous class. So let's take another convexity problem. So you have to check whether this function is convex or not, and we can have a similar approach that I have discussed before. So let's try to solve this. You can first write the gradient in this problem. So this is a three variable problem. This is 2x1. This term will be 4x3. Then you have 3x2. Then, yeah, you have probably this, I've written it twice. Okay, let's take this x3, x2. So I'll modify it. So you have plus 5 and you don't have any other terms. Next, x2 will give you something like 3x1, then minus of x3, and you don't have anything else from this side. And finally, you have in terms of x3, is 4x3 plus 4x1 minus of x2 minus of 7. So this is your gradient, and your Hessian will be uh, this will be 2, 3, 4, 3 minus 6 minus 1. This okay. Again close. This is 4 minus 1 minus 4. So in this situation, again, what you have to do is you have to check for the positive definiteness of this matrix H, and you can notice that it kinds of difficult to check that. But there are ways of checking it. Suppose you take two parts of it, like you can take all the determinants having 1 cross 1 kind of dimensions of those matrices, and this, and finally the entire matrix. And if you can ensure that all of these determinants are positive, then you can say for sure that your eigenvalues are positive and this is a positive semi-definite matrix. So let's try to do that. So every 1 cross 1 component here probably will not turn out to be like positive, but anyways, let's check with something different. So what you can do, you can take this portion of the matrix, and that will be suppose your H2. So this is minus 12 of minus 9, so this is minus 21. So this is less than 0. So again, this function will not be convex, that you can say for certain. And this you can also check by this determinant. If you evaluate of this function, probably will have a negative value, and probably you'll have one eigenvalues as negative in that case as well. And the trace of this matrix is the sum of the eigenvalues. So it's minus 6 plus minus 4 plus 2, so it's minus 8. So you can kind of guess that one of the eigenvalues has to be negative in order to have this summation to be negative. So yeah, you can say that this is, you cannot say for certain, like this is not a convex function for sure, and then uh, probably this will not even end up being a concave function as well. So yeah, so both of the statements will be incorrect in this situation. So let's see what I have after this. Okay, I have another example on convexity. Okay, so suppose I have to check whether a function, this fx minus e to the power x is convex or not. So let's do a similar approach. So this is a single variable function here. So this is kind of simpler. So what you can do, you can take the first derivative, and this will be same here in this situation. And the second derivative you can take again. So this will be again similar. And since e to the power x is always positive, you can say that this is less than 0. So this function again, it's not a convex function, that you can say for certain. Uh, because again, this part is kind of equivalent to the Hessian of your multivariable setting. Here, if your f double prime x is less than equals to 0, that means your function uh, might be having some maxima or something, but you won't be like having a minima point anywhere in if you are given some domain or something. Anyway, so you can have a similar problem like this. Suppose you are asked whether this function is concave or not. So suppose I ask you fx minus e to the power x is concave or not. So in the lecture, sir had already discussed that if one function is convex and you take a mirror image of that function, you kind of get a concave function. So the way you do it is just to take a negative value of it, and you can have fx equals to e to the power x. So this is equivalent to kind of finding out whether this is convex or not. So in this setup again, just to check the convexity, you can use this f double prime x and it will end up being probably positive. And you can say that this function is convex. And if you draw the graph of this function, you will probably get a convex function. Okay, so let's see what I can do. Yeah, so I can solve this problem or I can check the graphs that of the problems that I have discussed so far. So, okay, let's solve this Newton-Raphson's method problem. Then I'll be probably checking those graphs and conclude this session. So, in Newton-Raphson's method, you have an update rule, which is xt plus 1 xt minus fxt f prime of xt. So just be careful while using this Newton-Raphson's method compared to Newton's method. So in Newton's method, probably what you are asked is to solve for a minima of a function. So for that condition, your f prime x uh, naught or xt has to be 0. So that's why you have a first derivative in the numerator and second derivative in the denominator. But whenever you are asked to solve an equation, you have this kind of an expression. So again, what you can do, you can start with x naught equals to 1, and you need to have the first derivative of the function. So your fx is x minus 20 ln x plus 36, and your f prime x is 1 minus 20 by x. So if you just plug these values, you will get x1 equals x naught minus fx naught, fx1. So this part will be 0, so that will be 37. And in your denominator, you will have 1 minus 20 by 1. So this is minus 19. This is minus 19. And so this will be 56 by 19. So this will be your updated value of x1. Similarly, you can get to x2 and something like similar you can do. And whatever you have to do, you just have to replace this x value in this f prime x and fx, and you will just can use Excel or any other software to solve this problem. So again, this is a simple problem. I'm not solving it again fully, but you can use this similar approach. But here, I think I have asked like what will be the updated value after first iteration, and then also you have to probably have to find the update rule for this. So for that, you can do xt plus 1 equals xt minus fxt is given as uh, xt minus 20 ln xt plus 36, and this part will be 1 minus 20 by xt. So this will be your update rule for this. You can simplify it further, but it's not required, and you just have two columns in Excel and can solve it pretty easily. So yeah, this problem it's again pretty simple. So let's see what I have. Yeah, so this discussion on affine function, I think you have already gone through this in the lecture. But if you have doubts, like first of all, if you are taking a function like hx, and if you are having it in a convex optimization problem and with an equality constraint, so hs equals to 0, then for a convex optimization problem, you need to have this function as hxx, a convex function. So now this term, I can write it as hx greater than equals to 0 and hs less than equals to 0. So if we are having it in this form, then this is a convex function. And then this part is minus hx is less than equal to 0. If we're writing it in this fashion, then your minus hx has to be a convex function. On like similarly, you can say that hx is a concave function as well. So in order to have a function as both convex and concave, you can uh, have a function like this. This is a straight line. So if you take any 2 point on this straight line, it will lie, it would like coincides with that. So it does not like kind of lie below or uh, above the curve. So in case of convex function, we have something like this. In case of concave function, we have like this. In order to have it both convex and concave, you can just have a straight line. So affine functions are pretty like synonymous to straight lines only. So these are linear equations. Okay, so yeah, so you might get some single variable optimization problem in your assignment this week as well. So you have to be careful to solve such problems. So suppose I have this problem, fx. Let me see how much time I have. Okay, 8 minutes I have. So, any like Manohar is here only. So, do you have any questions related to assignment or anything? Otherwise, I'll just discuss this problem and probably conclude after that. Yeah, okay. So, suppose you have this kind of a function where x is greater than equals to 0 and a is a constant. We can have a greater than 0 or less than 0 or equals to 0. So let's do this. Suppose you have to optimize this function. You will take the first derivative. Then it will be your, okay, yeah, this will be your first term and your second term will be this. So if you take this as common, so whatever you're left with is 1 minus 2x. And then you can again take the second derivative of this function. So what you can have is 1, then 2x minus 2, and then you have this is minus 2. So in order to optimize this function, first derivative has to vanish. And since suppose a is not equals to 0 here, if a is 0, then this function becomes 0 itself. So that doesn't make any sense. So what you are left with, and since this e to the power minus 2x can never be 0, we are left with x equals to half. And if you plug it in here, then what you will get, this first term again, this part will vanish, this will be 0, and you will be left with minus 2a e to the power minus 1, yeah, minus 2a e to the power minus 1. So now, suppose you are asked about maxima or a minima. So depending on the value of a that is given in the problem, suppose a is positive. If a is positive, then your f prime x or f prime half, I can write. becomes negative, similarly, if A is negative, your double prime half, this is positive. So in this case, you will be getting a maxima, and in this case, you will be getting a minima. So you'll probably get, you can get similar problems like that. So just pay attention to the coefficients. Whenever you get a function like e to the power minus t, and then some coefficients, don't assume that you are solving some minimization problem or a maximization problem. So depending on the constant value, it might be different. Okay, so I had only this problems on my mind. So since I have 5 minutes more, let's see if I can show you some of the graphs that we have already discussed in this class and whether those were convex or concave or not. So let me unshare the screen. Okay, so I'll do that pretty quickly. Okay. Yeah, just wait for a couple of minutes. I'll have it ready. Okay. So, yeah, so yeah, share the screen. Probably I need to unshare this. Yeah, so what you can do, I think the screen is coming up. Uh, you can go to this website called graph.tk where you can put equations. So this y equals to say x to the power 6 times 1 minus x to the power 6. And as you can guess that if you take 2 points in this curve, that will kind of end up being lying outside of those curves. So this is not a convex or a concave function. You cannot say that for certain. So if you had taken it as if this as x to the power 6, you can say for certain that you take any 2 points and that curve will kind of lie below that. But again, I think what you have is, uh, yeah, take a similar approach. Take 2 points and that straight line, if it lies below that segment lies below that straight line, then it's concave. Otherwise, it's concave. Convex. So, and another example, I think, I don't know if whether the multivariable thing works here or not. Let me just try it out anyway. Yeah, so this part is, I think it's for only just for single variable. So I had minus e to the power x. So here also you can have see that this curve is concave because the curve lies above the straight line if you join them. And similarly, this part is convex. If you just have 2 points and join them by a straight line, the curve will lie below that straight line. So for similar problems, you can solve this using graph.tk, like for a single variable problem. But for multivariable problem, what you can do, probably you can plot it in Python or any other programming language if you know, and then you can check that as well. And probably there are some other online tools you can find and have this multivariable functions plotted as well. So just to be sure whether your function is convex or concave. So I don't have anything else. It's 4 already. So thank you. We can join the next session if we don't have any questions. So